Hey guys, welcome to our YouTube channel. In this video, we will discuss the story of a black hole, what spacetime is, and some information about gravity in simple words. But before starting the video, please give us a thumbs up and subscribe to our YouTube channel. Now let's get started. What are black holes? A region of spacetime in which gravity is so strong that no light can escape. Albert Einstein's theory of gravity predicts the existence of black holes. Black holes are some of the most fascinating objects in the universe. Black holes are dark, dense regions in space where gravity is so strong that nothing can escape. Not even light can escape from these areas. This is why we cannot see black holes. They are invisible to our eyes. Since nothing can escape from black holes, physicists are trying to understand these objects. Even the laws of physics don't tell us what happens when something falls into a black hole, at least not yet. Therefore, black holes remain cosmic mysteries, and many scientists are working hard to solve the mystery of black holes. To understand what happens to black holes, we first need to learn more about space and time. Few people understood space and time better than Albert Einstein, the famous physicist with wild curly hair. Although Einstein used advanced mathematics to develop his ideas about the universe, we can grasp the basic elements of Einstein's theories using pictures, analogies, and our imaginations. Analogies are valuable teaching tools in physics because they compare abstract scientific concepts with familiar concepts that we know from everyday life. What is spacetime? Let's start with general relativity, which is Einstein's theory that links space and time to gravity. This theory is based on Einstein's insight that we should not think of space and time as separate, but rather as connected elements that make up spacetime. Spacetime is our way of describing all events in the universe, where they happen and when they happen. For example, if you want to meet your friends after school, you need to agree on where you want to meet, place, and when time. Thinking of all the places and all the times in the universe together is conceptually challenging. The universe is so vast after all. How can we imagine spacetime? Spacetime flows like a river. Fortunately, analogy can come to our rescue when trying to understand spacetime. This analogy compares the structure of spacetime to the flow of water. Spacetime away from the planets and stars is flat and smooth without any movement, just like a great still lake. Objects and people can float freely in this lake. You can stay still, or you can easily swim in any direction. This scenario is similar to astronauts floating freely in space, where they can easily move up and down and left and right. This scenario changes when we look at the spacetime surrounding massive objects such as planets, stars, and black holes. Spacetime near these cosmic objects is no longer calm and smooth, but curved and swirling, just like strong streams or rivers. Just imagine that there are strong currents in certain parts of the lake. You cannot see or sense their presence when you are very far away from these currents because the water around you remains calm. But if you swim to another part of the lake, near one of the currents, you can start to feel the current pulling you along. Likewise, astronauts feel the gravitational pull of planets if they get too close. If the current is very weak, you are close to the current of a planet, like the spacetime around Earth. But the pull becomes stronger near a stellar river like the spacetime around our Sun, and much more intense near a stream of black holes. The closer you are to the current, the faster you must swim if you want to escape its strong pull. You have to make an effort to get back to the calm zone of the lake where you can stay calm and swim and sunbathe. The same is true of spacetime. The closer you are to a cosmic object, the harder it is to escape the gravity that pulls you to that object. A better explanation of gravity. The river analogy illustrates a key insight in Einstein's theory, namely that space and time are linked by gravity. Gravity is what makes apples fall from trees and what keeps you stuck to the ground. You probably learned that gravity is the attractive force between massive objects. The mass of the Earth pulls everything towards its center, and it is this pull that we associate with the force of gravity. This description of gravity is a pretty good explanation of what happens on Earth, but Einstein realized that an even better explanation could describe all gravitational processes in the universe, a spacetime explanation. According to Einstein's theory, gravity shapes the structure of spacetime. Massive objects like planets and stars tell spacetime how to curve, and curved spacetime tells these objects how to move. With the analogy of a river, this interplay between spacetime and gravity is easy to understand. Moving through spacetime is like swimming in water. If there is no planet or star, you are swimming in a lake. The water is calm, and you can float in it like an astronaut floats in space. Near the planet, water is like a river. You are pulled along with the river, just as a nearby object in space would be pulled down here on Earth. Einstein's theory of gravity was revolutionary because it offered a better way of thinking about our universe. General relativity also predicted the existence of black holes, which are regions where the spacetime current is so strong that nothing, not even light, can escape. It's like a cosmic one-way street. Objects can fall into a black hole, but nothing can ever come back. Weird, right? At first, Einstein thought black holes were too strange to be true. Maybe the equations were playing tricks on him, and he didn't quite understand them. But the longer Einstein and other physicists studied the equations, the more convinced they became that black holes existed. Falling into a black hole. Of course, we're not going to use equations to explain black holes to you. We will use the less complicated analogy of a river. Let's see how the river analogy helps us understand what happens when you fall into a black hole. Imagine you are back in the lake, and the lake is flanked by a river with a strong current. If you get too close to the river and do nothing, the current will pull you into the river. You start moving with the river, and your speed gradually increases. Maybe you get tired of being swept down the river and decide to swim back to the lake. However, you will notice that the further you are from the lake, the faster you have to swim to get back, and your effort depends on where you are. Escaping a planetary stream is easier than a star river, which requires more effort. But if you're in shape, you can always do it. Black hole torrents have a much stronger current than planetary currents or stellar rivers, and black hole torrents are special in another way. They form waterfalls. As you approach the waterfall, nothing seems strange or unusual. Your speed keeps increasing and you are carried further downstream. But once you cross the waterfall, you realize you can't go back. Even if you swim with great energy, you cannot swim back to the waterfall. The current is too strong and always pulls you away. Physicists observe a similar phenomenon around black holes and call it the event horizon. Just as a waterfall marks the point of no return in our imaginary lake, the event horizon marks the point of no return around a black hole. Instead of water, it's gravity that pulls you down and prevents you from coming back up. You can think of the event horizon as the surface surrounding a black hole. Anything outside this surface, including astronauts, rockets, or light, can escape from a black hole. But once this surface is crossed, nothing can escape, regardless of its speed, because of the strong gravitational pull towards the center of the black hole. Not even light can escape, and light is the fastest thing in the universe. Because light cannot escape, you cannot see what is inside the event horizon. It is like the horizon of the Earth beyond which you cannot see. This is why physicists are so fascinated by black holes. They know that objects continue to exist after they cross the event horizon. But scientists have no way to observe exactly what happens because gravity is so strong. Black holes and event horizons may sound mysterious at first. Fortunately, the river analogy helps us uncover part of the mystery. Thinking with analogies is a wonderful trick that many physicists use to explore complicated physics concepts. The river analogy is mathematically correct, but we don't need to understand the mathematics of spacetime to use the analogy. Instead of studying complicated spacetime equations, we imagine the spacetime around a black hole as a river. We then explore the properties of black holes and event horizons by imagining ourselves swimming in this river and falling down a waterfall. Naturally, such simplification can sometimes also introduce our imagination. This is why physicists need to combine their imagination with mathematics to fully understand the world around them. If you train your imagination and math skills, who knows, you might solve the remaining black hole mysteries that still puzzle physicists today. That's all from today's video. Please let us know your opinion about the video in the comment section, and tell us what knowledge you gained from today's video and what you knew about a black hole before. Don't forget to like and share the video and also subscribe to our YouTube channel. See you in the next video. Until then, take care.